Welcome back. In this video, you will learn about fluid pressure and fluid force as they relate to calculus. Let's get to it. All right, so the last application of definite integrals that we are going to take a look at in Calculus 2 is calculating the force exerted by a fluid on a vertical surface. But before we can look at that, we want to first discuss what fluid pressure and fluid force are by looking at a more basic case with a horizontal surface, which is not going to require any calculus. And so if you've ever been swimming in a pool or in the ocean, you've probably noticed that if you try to submerge an object into the water, that you start to feel some kind of pressure on that object. And the deeper that you submerge that object, the more pressure that you feel. And so that's what we're talking about here with fluid pressure and fluid force. In general, when objects are submerged in water or any other fluid, there is a pressure on that object from the fluid or the water. And the deeper the object is in that fluid, the greater the pressure will be. And this relationship is represented by this equation right here. The fluid pressure is equal to W times H, where W is the weight density of the fluid, and H is the depth of the object in the fluid. And so I have a picture over here of a surface that has been submerged horizontally in a body of water. And so the depth that that surface has been submerged to is H, the depth of the object in the fluid. Now for the weight density of the fluid, that is going to depend on what type of fluid we are working with and what measurement system we are working with as well. And so here I have a chart of the common weight densities of fluids that you might want to be aware of. We have our type of fluid in the first column, and then we have the weight densities of those fluids in newtons per cubic meter, which is if you're working in the metric system. And then we have the weight densities in pounds per cubic foot, which is in the imperial system or the US customary unit system, however you want to call that. And so depending on which unit system you are in determines which of these values you will use for each of these fluids. Now just note that these values can vary depending on the textbook or source that you're looking at, and so these are not exact values. They are rounded off a little bit, and so there is a little bit of leeway there where these values can change just a little bit depending on the source material. But I wouldn't worry about memorizing any of these weight densities besides water, because generally if you're not working with water, the weight density of the fluid you're working with is going to be given to you in a problem asking for you to find the fluid pressure or the fluid force. And so the only weight densities that I would recommend that you know are the weight densities for water in newtons per cubic meter and pounds per cubic foot. And so that's 9,810 newtons per cubic meter and 62.4 pounds per cubic foot. And so I would recommend that you learn these two weight densities of water because that's the most common fluid that you will see in fluid pressure and fluid force problems. All right, but back to our formula. We know, thanks to Pascal's principle, that the pressure exerted by a fluid at a specific depth h is transmitted equally in all directions for the surface. And so because of that, we know that fluid pressure is force per unit of area. And so let me show you how we know that. Remember that the fluid pressure is equal to the weight density of the fluid times the depth. And so if we write out the units for each of these variables, and I'm going to work with imperial units here, the weight density of our fluid is in pounds per cubic foot, and that will be multiplied by a depth, which is going to be measured in feet. And so this unit of feet is going to cancel out with one of these units of feet, and so we're going to be left with feet squared in the denominator. And so pressure is equal to pounds per feet squared. And remember that feet squared will represent an area, right? Cubic feet is a measurement of volume, and so feet squared is a measurement of area. And so since that is a measurement of area, and we know that pounds is a measurement of force, then the fluid pressure is equal to a force divided by area. And so that's what I mean when I say fluid pressure is force per unit of area, right? The pressure is equal to force divided by area. And so if I rewrite that here, the pressure is equal to force divided by area. If we multiply both sides by the area, then we can solve for the fluid force, right? So if we multiply both sides by the area, we will have that the fluid force is equal to the pressure times the area. And so then if you wanted to, you could replace the pressure with the weight density times the depth of the object in the fluid. And so you could say that the fluid force on an object is equal to the weight density times the depth times the area of that object or of that surface. And so for a horizontal surface, where that whole surface area is located at one specific depth, this is the formula that we can use to calculate the fluid force on that horizontal surface. And so to summarize, the fluid force on a submerged horizontal surface is this formula right here. The force is equal to the pressure times the area, and this is another way to write that, which is equal to the weight density of the fluid times the depth of the horizontal surface in the fluid times the area of that surface. And so let's take a look at an example problem where we can calculate the fluid force on a horizontal surface. So here's our example problem. We want to find the fluid force on the top of a rectangular metal sheet measuring 8 feet by 2 feet that is submerged horizontally in 8 feet of water. All right, so since our rectangular metal sheet is submerged horizontally in a fluid, which is water, we can use the following equation to find the fluid force. The fluid force will be equal to the pressure times the area, which is going to be equal to the weight density of the fluid, which in this case is water, times the depth that surface has been submerged into the water, times the area of the surface. All right, and so let's find each of these values. Let's start with the weight density of our fluid. And the weight density of water, when we're working with feet, meaning that we are working with imperial units or the US customary unit system, is going to be 62.4 pounds per cubic foot. And so we'll have that this is equal to 62.4 pounds per cubic foot, and that will be multiplied by the depth of the surface in the water. And remember that our metal sheet is submerged horizontally in 8 feet of water, and so the depth is 8 feet, so we'll multiply by 8 feet, and then we'll multiply by the area of our surface. So we're told that our rectangular metal sheet measures 8 feet by 2 feet, and so the area of the rectangular metal sheet will be equal to the length times the width, which in this case is just 8 feet times 2 feet, and so our area will be 8 feet times 2 feet. Okay, and so if we simplify, this will be equal to 62.4 pounds per cubic foot times 8 feet, and 8 times 62.4 will be 499.2, but then our units, this unit of feet will cancel out with one of the units of feet down here, and so we will have pounds per square feet. All right, and that will be multiplied by the area, which we have 8 feet times 2 feet. That will be 16 feet squared, or 16 square feet. And so then if we multiply 499.2 pounds per square foot times 16 feet squared, those units of square feet will cancel out, and then 16 times 499.2 will be equal to 7,987.2, and our units are going to be in pounds, since that is what is left over after the square feet cancel out. And so our units will be in pounds, which means that the fluid force on the rectangular metal sheet submerged horizontally in 8 feet of water is 7,987.2 pounds. And those units make sense because force can be measured in pounds when you're working with imperial units, such as feet. Okay, and so that's how you calculate the fluid force on a surface that is submerged horizontally in a fluid. But what if our surface was submerged vertically in a fluid? Well, when a surface is submerged vertically into a fluid, calculating the pressure on that surface is not going to be as simple as it was for a horizontal surface. Because when a surface is submerged horizontally in a fluid, the pressure is constant over the entire surface since it was all located at one specific depth value, right? But if you look at this vertical surface, there are a range of depth values for that surface. And so remember that the fluid force is equal to the pressure times area, and that is equal to the weight density of the fluid times the depth times the area, and that depth h is not constant for this entire surface, right? At the top of the surface, we are at a specific value of depth, but at the bottom of the surface, we are at a different value of depth. And so between the top and the bottom of the surface, we have all of these other values of depth, which means that the pressure exerted at those different depths on the surface is going to vary. And so because of that, the fluid pressure is going to be variable, which means that in order to calculate the fluid force, we are going to need to use calculus. And so how are we going to do that? How are we going to find a formula that will represent the fluid force for a vertical surface? Well, what we can do is we can look at the pressure on a representative rectangle of this surface. Right, so if I draw a representative rectangle right here, we can look at the force for this thin region of our surface and integrate that force for the entire range of depth values from C to D. And so if you imagine that we had a coordinate system here, let's say that this is the y-axis and this is the x-axis, and I'll label them, so this is the y and then this is the x. What we can do is represent the height and the area of this representative rectangle in terms of y. And I say in terms of y because if we're going to set up a definite integral here to represent the fluid force, we're going to be integrating between these two values of depth, C and D, which are going to be values along the y-axis. And so we're going to want to work in terms of y. And so let's start setting up our definite integral. The fluid force is going to be equal to the weight density of the water, which is a constant, so we're going to keep that outside of our integral, but that will be multiplied by the definite integral from C to D. All right, and then we need to determine the depth and the area of our representative rectangle in terms of y. Now the depth is going to be pretty simple. The depth is just a distance from the representative rectangle to the surface of the fluid. And so we're going to represent that as a function of y, which will be h of y. And so we'll put that into our definite integral. We will have the depth in terms of y, and then we need to multiply that by the area of that representative rectangle. Now the area of a rectangle is equal to the length times the width. And so if there's going to be an infinite number of these thin rectangular regions from C to D for this entire surface, then we'll say that the width of those rectangles is going to be a small change in y, which we represent with dy. And so that's the width of our rectangle, but then the length of the rectangle is going to depend on the length of our surface. And so we'll represent that with another function in terms of y. And so this distance right here will be the length in terms of y, which we represent with a capital L. And so then for the area in our definite integral, we will have the length times the width, which will be capital L of y times dy. And so we'll have capital L of y times dy, which represents the area of our representative rectangle. All right, and so that completes our definite integral. This represents the fluid force on a vertical surface submerged in a fluid. All right, and so to summarize, the fluid force on a submerged vertical surface, this is different from a horizontal surface, is equal to the weight density of the fluid times the integral from C to D, which are two values of y that represent the range of depth values for your surface of the height in terms of y for a representative rectangle times the length in terms of y for that rectangle times dy. Okay, and so let's look at an example problem where we will calculate the fluid force on a submerged vertical surface. All right, so here's our example problem. We want to find the fluid force on a rectangular plate measuring 3 feet by 5 feet submerged vertically in water to a depth of 4 feet. All right, and so the first thing that I recommend that you do for fluid force problems where you have a vertically submerged surface is draw a picture. This is going to really help you set up your definite integral. And so we know we have a rectangular plate measuring 3 feet by 5 feet. And so I'll draw our plate here. This rectangle will represent our plate. Its dimensions are 3 feet by 5 feet, so I'll label that. That is 5 feet. And then we know that it is submerged vertically in water to a depth of 4 feet. And so, if this is the surface of the water, then the distance from the surface to our plate will be 4 feet. All right, and so now that we have a picture drawn here, what we want to do to be able to set up our definite integral is set up a coordinate system for this picture. And so this is where fluid force problems can become a little bit tricky because there is not one specific way to set up your coordinate system to get the correct answer. There are a ton of different ways that you can set up your x-axis and your y-axis such that you can set up your definite integral. Now there's definitely going to be some ways that are easier than others, and that's what I'm going to try to show you here. I'm going to try to show you the best way to set up the axes, but in the end, it's all going to be about preference and how you like to set up these problems. And so I'm going to start by showing you one way to set up the coordinate system for this problem, and then I'm going to show you a second way that we could set it up. And you're going to see that we get the same answer both ways. And so the first way is we're going to let the surface of the water be the x-axis. And so I'll draw that. This is going to be our x-axis, and I'll label it. So this is the x-axis. And then we're going to let the left side of our surface be the y-axis. And so the y-axis will line up with the left side of our surface. So that is the y-axis. All right, and so now by doing that, we can now represent the range of depth values for our surface with values of y, right? We know that this surface is submerged to a depth of 4 feet, and that is this distance right here. So the top of our surface is at a depth of y equals -4, right? So this y value right here is -4. And then the width of our surface is 3 feet, and so the bottom of our surface will be at a depth of 3 feet lower than the top. So if the top is at the y value of -4, then the bottom will be at the y value of -7, right? That is 3 less than -4. All right, and so now that we have identified the range of values for our depth, we can start to set up our definite integral to calculate the fluid force for this vertically submerged surface. So remember, the force is equal to the weight density of the fluid times the integral from c to d of the depth in terms of y times the length in terms of y times dy. And so let's start setting it up. We know that the fluid in this problem is water, and so we are going to want to write down the weight density of water. And since we are working in feet, that means we are using imperial units, or the US customary unit system, which means that the weight density of water will be equal to 62.4 pounds per cubic foot, and that will be multiplied by the integral from c to d. And so those are our two values of y that the depth of our surface lies between. And so we just found those. The depth of our surface is going to range between -7 and -4. So we will integrate from -7 to -4. And then we need to determine the depth of our surface in terms of y. And so remember, we are looking at thin rectangular regions throughout our surface from the depth values of -7 to -4. And so how can we represent the depth of these rectangles in terms of y? Well, notice that the depth of this rectangle is going to be whatever value of y it is located at, right? So if this rectangle is 5 feet deep into water, it will be located at y equals -5. If the depth of this rectangle is 6 feet, then its depth will be the y value of -6. And so what we can do is represent the depth in terms of y as -y, where y is the depth of that rectangle, right? So whatever the depth is, that's going to be the value of y that we then negate to get that y value along the y-axis. And so now we can replace -y for h of y in our definite integral. So we will have -y, and then we want to multiply that by the length in terms of y. And so that's going to be the length of our rectangles, or the length of our surface. Now notice in this case that the length for all of the rectangles that we could draw between the two depth values will have the same length. Our surface is a rectangle, and so the length is going to be constant throughout the entire surface. And so we don't actually need to represent that with a variable such as y. We can just say that the length in terms of y is equal to 5, because that is the length of our surface for the entire surface. And so the length in terms of y is equal to 5. And so we can replace that in our definite integral, and we can multiply -y by 5, and then multiply by dy. All right, and so now we have finished setting up a definite integral that will allow us to calculate the fluid force on this plate or on this surface submerged vertically 4 feet into water. Okay, and so if I clean up my work here, let's solve this definite integral. If we pull this 5 and this negative out to the front of the integral, we'll multiply 62.4 by -5. That will give us that this is equal to -312 times the integral from -7 to -4 of y times dy. And now we have a much more simplified version of that integral that we can solve. And so if we integrate y by using the power rule of integration, we'll add 1 to the exponent and then divide by that new exponent. And so this is equal to -312 times y squared divided by 2, evaluated from -7 to -4. All right, and so we can evaluate this expression at -4 and subtract the evaluation at -7. So this will be equal to -312 times -4 squared divided by 2 minus -7 squared divided by 2. Okay, and so if I clean up my work again, the fluid force will be equal to -312 times -4 squared, which is 16, divided by 2, minus -7 squared, which is 49, and that is also divided by 2. And then 16 halves minus 49 halves will be -33 halves, and so this is equal to -312 times -33 halves. And if you multiply -312 times -33 halves, you will find that the fluid force is equal to 5,148. Now the units are going to be in pounds because we were working with feet, and the weight density of water that we used was measured in pounds per cubic foot, and so our fluid force will be measured in pounds. And so 5,148 pounds will be the fluid force on this rectangular plate that is submerged vertically in the water to a depth of 4 feet. And so that was just one of the many ways that we could set up a definite integral to find this fluid force. And so I just want to show you that there is no one correct way to set up your coordinate system and set up your definite integral. There's going to be an infinite number of ways that you could set up this problem and still get this same correct answer. And so that's what I want to show you real quick. And so let's back it up a little bit. I removed our x and y axis. And now what we're going to do is, instead of making the surface level of the water the x-axis, we're going to make the x-axis the bottom of our submerged surface. And so I'm going to let this be the x-axis, and I'll label it. So that is the x-axis. And I'm going to let the y-axis stay the same. I'm going to keep the y-axis on the left side of our surface. All right, there are times where I would recommend that you move the y-axis, and we'll look at that in our next example. But for now, I'm going to keep the y-axis on the left side of our surface. Okay, and so what we did was we moved the x-axis from the surface of the water to the base of our surface. And so our definite integral is going to look a lot different, right? So the fluid force we know is equal to the weight density of the water, or whatever fluid we're working with, times the integral from c to d, the two values of y that represent the range of depth values for our surface, of the depth in terms of y times the length in terms of y times dy. Now so far we can set up that this will be equal to 62.4, since that is the weight density of water in pounds per cubic foot. But then what about our bounds of integration? Well, since our x-axis is at the base of our surface, that means that the lower bound will be at y equals 0, and the upper bound is going to be y equals 3, since the width of our rectangle is 3 feet, right? So this y value will be 3, which means that the y value at the surface of the water is going to be 7 feet because of this extra 4 feet that we need to add to this 3 feet, right? So the surface of the water will be at y equals 7, and our range of depth values for our surface will lie between y equals 0 and y equals 3. And so we will integrate from 0 to 3. Now what about the depth in terms of y? How are we going to represent the depth of our representative rectangles throughout our surface? Well, the value of y that will represent the depth of this rectangle is going to depend on how far below the surface level of the water that rectangle is. And remember, the surface of the water is at y equals 7. And so if this rectangle, let's say it's 6 feet below the surface of the water, if we subtract that depth value from y equals 7, that will tell us that this rectangle would be at y equals 1, which would be 6 units below y equals 7, meaning it would be 6 feet deep in the water, right? So we subtract the depth of our rectangle, which we represent with y, from the surface level of the water, which is y equals 7. And so the depth in terms of y will be equal to 7 minus y. Okay, and so I'll replace that for h of y in our definite integral, and so we'll have 7 minus y, and then we want to multiply by the length in terms of y, which actually isn't going to change from the first way that we solved this problem. The length of our rectangle, or of our surface, is still going to be a constant value of 5 feet. So the length in terms of y is still going to be equal to 5, and so we'll multiply 7 minus y by 5, and then multiply by dy. All right, and so now we have set up a definite integral that represents the fluid force on this rectangular plate that is 4 feet below the water. Now it looks different from our definite integral from earlier, but what we're going to find is that if we solve this definite integral, we are going to get the same answer of 5,148 pounds. It doesn't matter where you set your x or y axis, as long as you determine the correct bounds of integration, your depth function, and your length function, you're going to get the same answer. And so let's solve this definite integral to verify that what I'm saying is true. Let's see if we get the same answer from this definite integral that we got from our previous definite integral for this problem. So if I clean up my work here, I'm going to pull out this 5 to the outside. 5 times 62.4 is 312. So this is equal to 312 times the integral from 0 to 3 of 7 minus y times dy. And now let's integrate each of these terms with respect to y. This will be equal to 312 times 7y minus y squared divided by 2, evaluated from 0 to 3. Right, the integral of a constant like 7 will be that constant times the variable of integration, which in this case is y, so we have 7y. And then the integral of y, if we use the power rule of integration, by adding 1 to the exponent and dividing by that new exponent, will give us y squared divided by 2. Okay, and so if we evaluate this expression at 3 and subtract the evaluation at 0, we will have that this is equal to 312 times 7 times 3 minus 3 squared divided by 2, and then we're just going to be subtracting 0, because if you plug 0 into this expression, you're just going to get 0. 7 times 0 is 0, minus 0 squared divided by 2, which is also 0, so this whole thing is just 0. And so if I simplify, this is equal to 312 times 21 minus 9 halves. And if I clean up my work here, 21 can be rewritten to be 42 halves. So this is equal to 312 times 42 halves minus 9 halves. And 42 minus 9 is 33. So this is equal to 312 times 33 halves, which gives us the same answer from before, that the fluid force is equal to 5,148 pounds. Right, so that is the fluid force on this plate that is submerged in the water, no matter how you set up your coordinate system. Okay, so we get the same answer either way. And so what I want you to understand here is that where you place your axes is completely up to you. It's all going to depend on what your preference is. Do you prefer to have the x-axis at the water level, or do you want to have it at the base of your surface? I personally prefer to put the x-axis at the water level because then the depth function h of y is pretty much always going to be negative y. You don't have to think too hard about what that depth function will be if you consistently set the x-axis at the water level. Alright, so certain ways of setting up your axes are going to be more advantageous if you're trying to solve your problems quickly without trying to spend too much time on the setup. Alright, but maybe you noticed that I didn't change the location of the y-axis, and that's because I wouldn't recommend that you change where that is unless you're working with a specific type of shape for your surface. And so that's what I want to look at next for our final example for this video. Alright, so here's our last example. We want to find the fluid force on the vertical side of the tank shown below where the dimensions are given in meters. Assume that the tank is full of water. Alright, so here's our vertical side of the tank. It's already given to us. We don't need to draw it. It is a trapezoidal shape where the height is 3 meters and the top length is 4 meters and the bottom length is 2 meters. Alright, and so the first thing that we want to do here is set up a coordinate system that is going to allow us to set up a definite integral to calculate the fluid force on this side of the tank. Alright, and so I want you to notice something before we even place down any axes. Note that the length of this trapezoid is not going to be constant, right? The length at the bottom is 2 and the length at the top is 4. And so when we are choosing representative rectangles between the range of values for the depth of the water in this tank, the length of those rectangles is going to change. And so when you have a surface submerged vertically in a fluid that is shaped like this, where the length will not be constant, and you see that the shape is a symmetrical figure, I would recommend that you place the y-axis in the middle of that shape. And I'm going to explain why, but let's set up our axes. We are going to put the y-axis right down the middle of this surface. And so this will be our y-axis, and I'll label it. So this is the y. And then we also need to place an x-axis, and I'm going to place it at the surface level of the water, right? Remember that this is the side of a tank that is full of water. So in this case, we aren't submerging an object into water. We have the side of a tank that is full of water, where that water is still putting pressure on that side of the tank. Okay, so the surface level of the water is going to be at the top of the tank. And so that's where I'm going to place our x-axis. This line right here will be our x-axis. All right, so I'll label that with x. Okay, and so now that we have added our axes, I want to label a couple points on our trapezoid, right? So if the top length, I kind of covered it, but the top length of our trapezoid is 4, which means that if we split it evenly with the y-axis, that this x value right here will be x equals 2, and this x value right here will be x equals negative 2. And then at the bottom down here, if the length across the bottom is 2, then this x value will be x equals positive 1. So we'll have 1 right there. And this x value will be x equals negative 1. So this is negative 1. And then since the height of our tank is 3 meters, that means that this y value right here will be y equals negative 3 because we're below the x-axis, right? So this y value right here will be y equals negative 3. Okay, so keeping all those values in mind, let's start setting up our definite integral to calculate the fluid force on this side of our tank. And so the fluid force is equal to the weight density of the fluid, which in this case is water, times the integral from c to d, the two values of y that represent the range of depth values of the depth function in terms of y, times the length function in terms of y, times dy. All right, and so in this case, we're working with measurements in meters, and so the weight density of our water is not going to be 62.4 pounds per cubic foot, it's going to be 9,810 newtons per cubic meter. So our force will be equal to 9,810 times the integral from c to d. Now in this case, what are the range of depth values for our tank? Well, if we look at our coordinate system here, the surface level of the water is at y equals 0, and so that's the highest value of y, where we could choose a representative rectangle within this surface, and the lowest value will be at y equals negative 3. So the range of depth values is from y equals negative 3 to y equals 0. So our bounds of integration will be from negative 3 to 0. Okay, and so then what about the depth function h of y? How are we going to express the depth of a representative rectangle for this surface? Well, remember, if we're looking at a representative rectangle for this surface, and we set the x-axis at the surface level of the water, then that means that our depth function, h of y, will be equal to negative y. That's the advantage of making the x-axis the surface level of the water. The depth function is going to be very easy to determine. Whatever the depth of your rectangle is, let's say it's 2 feet deep, that means that the y value that is located at will be negative 2. Okay, so that's how this function works, and so that will be h of y, our depth function. So I'll plug that into our definite integral. We'll have negative y times the length function in terms of y. Now this is where things are going to get a little tricky, but you're now going to see why I decided to place the y-axis through the middle of our surface. Right, I said it was because of symmetry, but now you're going to see why that symmetry is important. Right, we discussed earlier that the length of our rectangles throughout this whole region of this surface is not going to be constant. The length down here is shorter than the length up here, and so all the way through this region, that length is changing. And so what we can do is find the length in terms of y from the y-axis to this side and multiply it by 2, and that will give us the length in terms of y for our rectangles for the whole surface. Right, so if this distance right here we represent with x, then we can say that the length in terms of y of our rectangles is equal to 2x. Right, since this surface is symmetrical, this distance x is also going to be on this side, which means 2x represents the entire length of our rectangles. Now, what is x though? How can we represent x in terms of y? Well, what we need to do is find an equation in terms of y that represents this line right here. And what we can do to find that line is use a little bit of algebra by taking the two coordinate points that this line passes through, finding the slope between those points, and then setting up an equation for that line. Right, so this side of the tank, or this line, passes through this point right here and this point down here. The top point is located at the coordinate point of 2, 0, so that's 2, 0, and this point is located at the coordinate 1, -3, and so that is 1, -3. And so what we can do is find the slope between those 2 points, and then use that slope and one of these points to set up an equation of that line. So remember, the slope is equal to y sub 2 minus y sub 1 divided by x sub 2 minus x sub 1, or in other words, the change in y divided by the change in x. And so if we use our two coordinate points, that will be equal to 0 minus -3 divided by 2 minus 1. Right, so if we look at our 2 points, we have this y value minus this y value, 0 minus -3, and then we have this x value minus this x value in the denominator, and so we have 2 minus 1. And so if we simplify, this is equal to positive 3 divided by 1, which is equal to 3. And so the slope between these 2 points is positive 3. And so we can just say that the slope m is equal to 3. And then we can set up an equation to represent that line by using one of these points and that slope with the point-slope form of a line. Right, so remember, we can set up an equation of a line using the point-slope formula that y minus y1 is equal to the slope times x minus x1. Okay, so I'm just going to choose this point right here, 2, 0, and so the y coordinate is 0, so we'll have y minus 0 is equal to m times x minus the x coordinate, which is 2. And remember, we said that the slope is equal to 3, so let's plug that in. I'm going to replace m with the slope of 3, and so then if we distribute 3 through this quantity, we will have y is equal to 3x minus 6. Okay, and so this equation right here is the equation of this line, which would represent the distance from the y-axis to that outer edge. And so, in order to use that in our length function, we need to solve for x. We need this equation of this line in terms of y by solving for x, and that will allow us to find the length of our representative rectangles. Okay, so if I clean up my work here, let's solve for x in this equation. I'm going to add 6 to both sides, and so we'll have y plus 6 is equal to 3x, and then dividing both sides by 3 will give us that x is equal to y divided by 3 plus 2. Right, 6 divided by 3 is equal to 2. And so now we have this equation for this line in terms of y, and so we can plug that in for x in our length function, and that will give us the length of our representative rectangles in terms of y. And so we will have the length in terms of y is equal to 2 times y divided by 3 plus 2. And so we can replace this function for L of y in our definite integral, and so we will have negative y times 2 times y divided by 3 plus 2 times dy. And now we have completed our definite integral that represents the fluid force on this vertical side of the tank. All right, and so if I clean up my work here, let's solve this definite integral. So I'll start by pulling out negative 2 to the outside. So 9,810 times negative 2 will be equal to negative 19,620, and that will still be multiplied by the integral from negative 3 to 0 of y times y divided by 3 plus 2 times dy. Now if you distribute this y through this quantity, we'll have y squared divided by 3 plus 2y. And so let's do that. This will be equal to negative 19,620 times the integral from negative 3 to 0 of y squared divided by 3 plus 2y, and that will be multiplied by dy. Okay, and so now we can integrate each of these terms by using the power rule of integration. We'll add 1 to each of the exponents and then divide by those new exponents. And so this will be equal to negative 19,620 times y cubed divided by 3 times 3, right? We added 1 to the exponent to get 3, so we need to divide by another 3. So we have this 3 times another 3, plus 2y squared divided by 2, because we added 1 to this exponent to get 2, so we divide by 2, and that will be evaluated from negative 3 to 0. Okay, so if I clean up my work here, we can simplify, and this will be equal to negative 19,620 times y cubed divided by 9 plus y squared, since these 2's will cancel out, and that will be evaluated from negative 3 to 0. Okay, so now we can plug 0 into this expression and subtract the evaluation at negative 3, but note that plugging 0 into each of these terms is just going to produce 0. 0 cubed divided by 9 is 0, plus 0 squared is still 0. So we'll have that this is equal to negative 19,620 times 0 minus plugging negative 3 into this expression. So we'll have negative 3 cubed divided by 9 plus negative 3 squared. Okay? And remember to put those terms in parentheses so that you distribute that negative to each of those terms. And so then this will be equal to negative 19,620 times negative 3 cubed. That will be negative 27. So we'll have negative 27 divided by 9 plus negative 3 squared, which is positive 9. So we'll have 9, and we'll close that. But then negative 27 divided by 9 is equal to negative 3. And so I'll rewrite that to be negative 3. And then negative 3 plus 9 is positive 6, but that will become negative. And so we can rewrite all of this to just be negative 6. And so we're multiplying negative 19,620 by negative 6. And if we do that, that will be equal to positive 117,720 newtons, because we're working in terms of meters or the metric system, and so we need to use the metric system units for force, which is newtons, right? The weight density of our water was 9,810 newtons per cubic meter, and so we need to remember to continue to use newtons, not pounds, as our unit of force. And so that is the fluid force on this vertical side of the tank. Okay, and so hopefully you can see from this example that if the length throughout the entire surface is not constant, and your surface is symmetrical, that you should place the y-axis in the middle and take advantage of that symmetry to easily find the length of your representative rectangles and efficiently set up your definite integral to calculate the fluid force. Okay, so that's all I had for this lesson. If you want to see some more example problems, feel free to check out my examples video that I'll have linked at the end of this video as well as in the description below. If you have any questions, feel free to leave those in the comments, but if you don't have any questions, this is all I had for now, so I will see you next time.